Hello and welcome, class. Today we are going to be finally getting into a new chapter, Chapter 3. So, new number, not entirely new content. In Chapter 2, we just finished discussing not only the construction of the atom via subatomic particles. In addition, we talked about how atoms can vary if the subatomic particles themselves vary. So different neutrons give us different isotopes, different numbers of electrons give us ions. But on top of that, on top of the actual construction of the atom, we also talked about how we count atoms using the mole. So this is all well and good. What we are going to be talking about today are the properties of light that at least we here at the general chemistry level are going to be concerned about. And it may seem like a little bit of a tangent, but really if we want to round out our discussion of the atom, we need to understand at least the basics of how light behaves. This is going to be incredibly important for the discoveries around the electron that we're going to be getting into and quantum mechanics. So we're not going to be going, real hard into quantum mechanics, but we are going to be scratching that surface a little bit so we can get a deeper understanding for what it means to be an electron, and then we can also better understand the reactivity of atoms. All right, so we are currently in the late 60s, early 70s for pages in the textbook, so if you are reading along, please be aware that as I am discussing certain properties of light in the textbook, there are additional pieces of information that I'm kind of jumping over. That's a conscious choice. I don't think that the things that I'm skipping over really are important for the story that I am trying to tell, but there is more information if you would like to get more information on additional properties that we're not necessarily discussing. All right, so what is light? Well, light is a segment of what we call the electromagnetic spectrum. This is the continuous range of all radiant energy, including things like various waves, like radio waves and microwaves, light, so UV light, infrared light, and visible light, as well as all of the rays, so X-rays, gamma rays. Is there really a difference between waves, light, and rays? Not particularly, other than where they are found on the electromagnetic spectrum. All right, so down below we can see the full electromagnetic spectrum ranging from the high energy gamma rays all the way down to the low energy radio waves. And the visible light spectrum is right in here. It's a tiny, tiny little section of this spectrum ranging from around 400 nanometer wavelength light, which is purple, all the way to 700 nanometer wavelength light, which is red. And on the electromagnetic spectrum, it would appear as though the rays are these high energy components. What we call light is the kind of intermediate wavelength, segments of the electromagnetic spectrum, and the waves, including microwaves, which sometimes get included on the diagram, sometimes don't, just because they have a lot of overlapping characteristic with infrared and radio waves. Some physicists don't consider microwaves to be like a unique spectrum or section of the spectrum, but otherwise microwaves would be kind of right in here between the infrared and the radio. So the waves are the low energy forms of light. Other than the kind of arbitrary cutoffs for where like gamma rays become X-rays, like really there's not a hard line right here. It's more of a general kind of vague in between. So like there are certain segments of light, particularly if we're looking at something that has a wavelength of 1/100th of a nanometer, it's going to have some characteristic of gamma rays, some characteristic of X-rays. Again, it's not like a hard boundary, it's more or less a like soft cutoff. All right, so let's clear this a little bit and talk more about the different segments of the electromagnetic spectrum. All right, so we're going to start with the high energy. So we're going to start with the gamma. We're going to give a little bit more, of a meaning to what each of these waves really represents. So the gamma ray, which we also represent with the Greek letter gamma, is again the most energetic, and it can be found out in the universe, right, in the wild, even though it is incredibly high energy, in really one of two places. First, they are produced by supernovae. Supernovae being the plural of supernova. So if there are multiple supernovas, you have a collection of supernovae. And as basically stars explode, collapse, die, whatever the technical wording you want to use, the energy that is released from this is in the gamma range of the electromagnetic spectrum. Now, the second is something we've actually already talked about, radioactivity. So as a radioactive material decomposes, the energies that are given off are gamma rays, alpha rays, and beta rays. And the alpha and the beta we've talked about already, being those are like pieces of material. They are particles with a positive and negative charge, but that gamma ray is actually a high energy wave that can be found on the electromagnetic spectrum. All right, next up we have X-rays. The X-rays are predominantly, at least the most useful for us, in medicine, as well as like harnessing certain energetic fuels, or harnessing them for energy to be used. But medicine is the most, I guess, familiar, right? If you're taking an X-ray, what you're doing is taking a picture of the inside of your body. Now, X-rays can be pretty dangerous chronically, and that is also true for the gamma rays. Because these are, again, such high energy sections, these can be potentially dangerous with long exposure. Now, what does it mean to be exposed for a long period of time? It's going to depend exactly on what the energy level of your gamma or X-ray is. So the more energetic, the shorter time it takes for you to reach like dangerous levels of exposure. This is why if you're getting, let's say, an X-ray at the dentist or at the doctor's office, they oftentimes, even today, will drape you with like a lead apron. That way the stray X-rays are not going to permeate sections of your body that you don't actually want the X-rays to be going into. It's really going to be a focused beam, short-term exposure where it needs to be, and then no more than that. All right, UV light. The light section of the electromagnetic spectrum, and we're going to be talking about UV light first. These are the wavelengths of light that we really encounter here on Earth. So the highest energy UV rays, or UV light waves, which again, kind of somewhere between this cutoff between X-ray and UV. The highest energy ones don't really break through our atmosphere. The atmosphere actually does a pretty good job at filtering them out, but the two forms of UV light that do make it through are known as UVA and UVB. Now, UVB is what we would consider to be the worst. It is higher energy than UVA, so it is what is attributed to giving people skin cancer, right? If you're out tanning for too long, you're going to introduce the chance for like mutation in your skin cells, and the UVB is really what, after, again, chronic exposure, we have been able to link to skin cancer. However, UVB is not all bad. UVB is also what causes the production of vitamin D in your body. So actually getting outside and getting sunlight is really good for you. It's what your body then naturally uses to produce vitamin D, which is something that is essential for us to, live and be healthy. So UV light is good in small doses. This is what gives you, right, that production of vitamin D, but is very bad in long doses, which is what gives you the chance for contracting skin cancer. UVA is low energy enough that it's kind of the border of the purple light here. So this is where UVA light would be relative to purple light. And fun fact, there are some people, it's like a really rare mutation, but some people actually have 4 cones in their eyes instead of 3, like most people do. The cones in our eyes can detect red, green, and blue light, but there are people with that rare mutation that have a 4th cone, and what that 4th cone is purple light. If you are a person with that rare 4th cone, you actually are able to see into the UV range a little bit, and you would be able to pick up UV light, specifically UVA light. Now, if you see UVA light, you probably would never even realize it because it's just an additional shade of purple. Like the world might look a little bit more purple to you. But even saying that, it's just your world will look more purple compared to a person who doesn't have that fourth cone. Like, you would never realize the difference, right? It's like that philosophical question, is my red the same as your red? I don't think we'll ever find what the answer to that question is, but it's a really fun question to think about. All right, so speaking of cones and rods, that is what in our eyes enables us to see the visible light spectrum. We've just talked about what happens if you have an extra cone in your eye. You can actually see extra wavelengths of color. If you are missing cones, this is what leads to color blindness. So if you only have 2 cones, or maybe one of your 3 is not functioning at the same capacity as someone else's, you are going to be missing certain wavelengths of color. And so you're going to end up with like red-green color blindness or red-blue color blindness, all depending on which of your cones is possibly like malfunctioning or not present. Now, on top of the cones in your eyes, which allow you to see color, there are also what we call rods. These are what allow you to see light intensity. So how bright something is. White light versus no light, which we could also call black light. Not to be confused with UV light, different kind of black light, right? So how sensitive are your eyes to light? That's going to be proportional to the number of rods that you have. So if you're not staring at the sun, if you're taking care of your eyes, if you're eating your vitamins and minerals, your cones and rods are going to be performing at like top performance. Now, I remember learning when I was little, like, carrots are really good for your eyes. And the reason why is if you eat a lot of carrots, you're actually going to help nurture your rods a little bit, and you'll actually be able to see in the dark a little bit better because your eyes are going to be more sensitive to the light. All right, so next up we have the infrared. So this is our last section of light that we really experience with any great regularity, like here on Earth. Infrared is what we call also thermal energy. It is not just radiant energy in the sense that it's light, but it is also something that we feel. It is heat. So if you have like night vision goggles or thermal imaging capabilities on your camera, really what those pieces of technology are doing is picking up the infrared. They're picking up the heat in the world around you and then translating it into the visible spectrum so you can actually see it. If you because like regularly we can't see thermal light, we can't see the infrared, we can just feel it. This is actually how the infrared spectrum was was kind of initially discovered. The first segment of light that was discovered outside of the visible was the infrared. If I'm remembering the story correctly and with no specific details, it was Sir Isaac Newton who discovered infrared light because he was trying to study the optic properties of light. And so what he wanted to do was figure out which section of the visible light spectrum, which according to all they knew when he was alive, that was the electromagnetic spectrum. He broke white light up using a prism and put down a piece of paper underneath the like rainbow that had been created. And so from this prism, the light came in, light broke up to the different rainbow, and there was a piece of paper here with the rainbow broadcast down on it where it was like, red, orange, yellow, green, blue, purple. And he let it sit there for a while. And he wanted to see then, upon touching the paper, which band felt the hottest. And what he actually found is that the visible spectrum did not produce heat. No band on this piece of paper actually felt warm. It was actually just to the left of where the red was, where we now call the infrared, that actually felt warm. And so he reasoned that there must be a section of this greater electromagnetic spectrum that carried heat that we could not see. And so, after those initial experiments, we started expanding our experiments a little bit more, trying to find additional sections of the electromagnetic spectrum. All right, microwaves, again, not explicitly listed here, so I'll rewrite it, microwave. The microwaves are, I guess, most famously or infamously associated with the appliance of the same name, the microwave. And that is because the appliance, the microwave, uses microwaves to heat food. Now, we had just said that thermal energy, heat, is infrared. So it's also kind of like important to acknowledge that the consequence of this is that microwaves don't heat your food via heat. what they actually do is get absorbed by water. So if your food has any type of water inside of it, the bond length here, this OH bond length, is actually the perfect length to absorb microwaves. So if you're pumping in microwaves like into an object that has water, the water molecules are actually going to absorb all of these microwaves. It's going to cause them to wiggle a little bit more. So because they're wiggling a little bit more, they're going to start like rubbing up against each other. They're going to start introducing more friction inside of the object, and that friction is going to be what heats the food. So this is why in your like microwave, after you're done heating food, there are a couple of like dead spots where like the food is still cold. There are other spots where the food got more like heated, and you have to, like pause, stir it, put it back in for an additional minute, etc. It's because inside of your microwave, there are also dead zones where the microwaves are canceling out. And so the food in that particular spot is not actually going to get quote unquote heated because there are no microwaves hitting or exciting the like water molecules inside your food. This is also what leads to certain dishes, like plastics, being not microwave safe. It's because there are certain plastics that also interact with microwaves and would cause them to either melt or leach into your food, and you don't want to be eating that plastic. That's going to be terrible for you. All right, last but not least, we have radio waves. Radio waves, also popularized and associated with what they're most commonly used for, radio. Sound waves are actually like concussive. They're mechanical, they're physical. You like sound transfers by one object vibrating and passing that motion onto another object, passing it onto another object, which eventually will hit your ear. Well, radio waves are electromagnetic. These are radiant pieces of energy. They are not actually like concussive sound waves. So how radio waves work, why we use this section of the electromagnetic spectrum, and again, in no certain details, I am not an engineer, what radio waves are useful for is actually like encoding sound waves into them and transferring them over long distances. So it's like we can take the pattern of this like concussive wave, this sound wave, translate it into a bunch of like ones and zeros. These ones and zeros get translated into radio waves, which then get broadcasted out. And somewhere on the other side, we're going to have some type of satellite which picks up on each of these waves, brings it back into a piece of technology, decodes all of those ones and zeros, and then replays it as some type of audio wave, like an actual sound wave. The reason why we've picked radio waves for this process to get information from point A to point B is specifically because they are so low in energy. They are very unlikely to be disrupted by any other objects. They're not going to be absorbed by any other objects or like deflected or destroyed. It's because they're so low energy, they just kind of hang out floating from one location to another location until it's picked up and then decoded on the other side. All right, so that is our electromagnetic spectrum from gamma all the way down to radio waves and some associations that we can make with them, just so we have a little bit, again, of like a foundation, a context, a grounding for what each of these sections of the spectrum are useful for, like what we associate with them. All right, so the general properties of each of these segments of the electromagnetic spectrum are fairly similar. The characteristics that we are going to be introducing here are the wavelength, which is the length of the wave represented by this Greek letter lambda. Frequency, which is the duration, how long the wave takes to pass from one place to another. This is represented by Greek letter nu. And last but not least, amplitude. Amplitude, we are not going to be focusing on too much, but I do want to introduce the amplitude as a basic definition. This is the height or the intensity of the wave. So this is how bright the light is going to be. Wavelength and duration are not the same thing as intensity. So the wavelength is how long the wave is from one crest to another crest, or from one trough to another trough. So we can see this red light up on top. I'm just going to label this with an R for red. The wavelength appears to be this long. however many tick marks are in between. We're just looking at everything being kind of relative here. The blue light down below, from one peak to peak, we can see is a little bit shorter on this like measured scale up on top. So for this reason, we would say that the blue light has a shorter wavelength than the red light, right? The distance from peak to peak is shorter. Now the frequency, again, is how quickly it takes for the light to actually pass from one point to another. The wavelength and the frequency are inversely proportional. In other words, the longer the wavelength, the more time it takes for the wave to pass. So the lower section down below, this is the like frequency measurement. This is the time. So we can see that the blue light, because it is shorter in a particular time frame, let's say we're just looking at, like the same time frame here, we'll just cut it off. So the red light takes this much time, like 0.8, in order for one peak to pass, one cycle of the light. In that same amount of time, we have 1, 2, and a little bit extra of the blue light that has passed. So the blue light has a shorter wavelength and as a result can pass more quickly from one place to another. It has a higher frequency. So low frequencies give high wavelengths, and the opposite is also true. All right, so this inverse relationship between wavelength and frequency is also true because of what we call the speed of light, which is represented by the variable c. Now this is the distance that light can travel inside of a vacuum. All light, provided that it is traveling in a vacuum, travels at the exact same speed. Our speed of light c is equal to 2.998 times 10 to the 8 meters in every second. So for every 1 Mississippi, some wavelength of light has traveled, 30 million meters. That is an incredible distance. That is so fast. And because all light travels at the same speed, the wavelength of light and again, the frequency being inversely related, we can actually see are actually just exactly, like you multiply the two and that's exactly equal to the speed of light. So the multiple of wavelength and frequency is equal to the speed of light. That's what this equation is saying. So if you increase the wavelength, you have to decrease the frequency in order to keep this constant a constant. This is a way to explain that inverse relationship. Okay, so on the right-hand side, we have it's a little bit of like a joke, a meme that was spread around Tumblr so many years ago when I was actually on Tumblr and in graduate school to pass the time. And I think it's actually, or I thought it was actually a pretty applicable explanation to like not only the speed of light, but also our interest in studying light in the first place. So the universe introduces mankind, says, okay, you're a human. I gave you free will and a conscious mind, so you are free to do whatever you want. What do you want to do? The human says, go fast. And the universe says, okay, well, you're a perfect pursuit predator, but if that's the way you want to evolve, like, go ahead. The human, climbing on top of a horse, go fast. The universe says, wait, what? The human, subsequently inventing the carriage, the car, the bullet train, go faster. And the universe says, I implore you to stop. The human, currently trying to figure out light speed travel, faster. We have always been so, again, curious and intrigued at trying to not only observe the world around us, but harness the world around us for whatever means we want. And I just find it so fascinating that it is true. One of the technologies that we have persistently continued to try and work with and evolve and improve is how we travel. We want to be able to go from one place to another and not be inconvenienced by this travel. So we are currently trying to figure out light speed travel, a way that we could ultimately go from one place to another, again, 1 Mississippi, and we're suddenly somewhere else. That is the ultimate goal for trying to improve and optimize like our means of travel. And who knows, maybe we'll get there, maybe we won't. There is some some physics that concludes that we will never be able to reach light speed travel, but there are also other derivations in physics that have found some loopholes to the laws of the universe. Sure, we can't accelerate to light speed travel, but what if we took advantage of something that was already going faster than light? Would we be able to harness that? Or could we build a machine, let's say, that uses black holes to pull us instead of us throttling up to light speed? Would that work? And this is actually a realm right now of like physics and engineering that we are currently and very we are currently pursuing and like with great passion. All right, so we've introduced a variety of wavelengths of light in the electromagnetic spectrum. We have introduced how wavelength and frequency play off of the speed of light, given a little bit of context as to why we care so much about trying to, even just from an engineering perspective, like why we want to observe light and figure out how it works. So let's work through this example problem here to kind of tie things a little bit more quantitatively together. So if the radio waves transmitted by a local radio station have a frequency of 90.9 megahertz, because yes, all of those numbers on your radio dial actually do have a unit, and the unit is the megahertz, what is the wavelength of that radio wave in meters? All right, we also have a little hint here that 1 hertz is equal to 1 inverse second, so we can see how the hertz relates to the SI unit of the second. All right, I would encourage you to, again, pause the video, attempt this problem for yourself, where, as a hint, we're going to be using C is equal to lambda nu in order to rearrange and solve for lambda. All right, welcome back from unpausing the video. Let's start inserting what we know and use it to find what we are looking for. So the speed of light is a constant, and yes, the assumption we make with the speed of light is that it is equal to 2.998 times 10 to the 8 meters per second in a vacuum. But for all intents and purposes, we're just going to assume that there's a vacuum here. Sure, the wavelength might be a little bit off if we're making this assumption, but it's going to be close enough for our purposes. All right, so we can see that the speed of light is presented to us in the unit of the meters and the inverse second. Now our answer that we're trying to go for, the wavelength, is in meters, so check. We don't need to do anything to the speed of light. We're also given a frequency in inverse seconds, and it looks like the speed of light also has the second present, so we're just not going to touch the speed of light. The speed of light is going to be equal to lambda, again, what we're trying to find, and we're going to multiply this by our frequency. Now, the frequency that we are given is currently presented in megahertz, and if 1 hertz is 1 inverse second, it would appear as though we have a mega inverse second. 90.9 megahertz. We are going to now set this up, trying to get this into seconds, right? We currently have 90.9 mega inverse seconds, but we just want the inverse second. We want to get rid of the mega. So that's what we are going to do first. According to the metric prefixes, yes, the mega is not one that we in this class use frequently, so we don't really need to know it off the top of our heads, but we can still look up this information whenever we need, either by looking it up in the textbook or simply Googling it. So the megahertz to hertz, there are 10 to the 6, or 1 million hertz inside of every one single megahertz. And now we are going to get out of the unit of the hertz, since the megahertz here are going to cancel out. There are, according to our little conversion up above, 1 inverse second per every 1 hertz. So yes, the numbers here, 1 divided by 1, just give us 1, but it's also important to recognize where the units are going to be canceling out. So I'm going to explicitly include it in this calculation here, in this dimensional analysis. All right, so all we have to do then is take 90.9, multiply it by 10 to the 6. What we find is 9.09 times 10 to the 7 in proper scientific notation, and the unit that remains is the inverse second. So this is going to be what we insert then into our equation up above. Our speed of light is going to be equal to lambda, the wavelength we're looking for. We're going to multiply that by 9.09 times 10 to the 7th inverse seconds. All right, all we have to do then is rearrange and solve for lambda. Since the units that we can see on the left and the right are all now kind of playing together, there is the inverse second on our frequency, meaning that there should only be a meter present on the lambda. All right, so let's divide each side by the 9.09 times 10 to the 7th inverse seconds. The inverse seconds cancel out. 9.09 times 10 to the 7th inverse seconds. The 9.09 cancels out, as well as the inverse seconds. This gives us a final lambda that I'm just going to write all the way down here, so I actually have space to write the number. That is equal to 3.30 meters. So this is around 10 feet, right? The wavelength from peak to peak of this particular radio wave that is delivering to you music through your car's radio at the frequency of 90.9 megahertz is equal to approximately 10 feet, 3.30 meters. So one really great question is, if this wavelength of light is so big, right, 3.30 meters, we can see buildings that are 10 feet tall, we can see vehicles like trucks that are 10 feet long. Why can't we see this wavelength of light? If we look at it with our eyes, here's my little eyeball right here, why can't we see this? The answer to that question is the wavelength of light is actually too big. It's not a physical object that we're seeing, it's a piece of energy. In order for our eyes to be able to process a wavelength this large, they would have to be the size of a satellite dish. They would have to be so large in order to actually accommodate this very huge wavelength of light, particularly, again, because it's such a low energy piece of light. So we have wavelengths of light in the electromagnetic spectrum that are around us all the time, and we just don't know it or don't ever think about it. Like, if you feel the warmth of the sun, you are feeling the infrared. If you are listening to the sounds, like from a radio station, either like out of a boombox or your car or whatever the situation is, just know that there are radio waves around you. Even though you can't see them, we can turn them into sound waves and we can hear them. All right, couple of additional properties that we need to talk about before calling this a lecture. The big one, this is going to be our transition property, is the diffraction of light. So light is, because it is, waves, it is able to bend. So the diffraction of light is known as the bending of light, right? Electromagnetic radiation is just the big fancy word for light. So it's the bending of light as it passes around the edge of an object or through some type of narrow opening. So if the gap is fairly wide, which is what we can see here on the left, right, a wide gap, the waves, which this is a top-down view, so we can imagine like this piece right here as like the shore, and the like blue lines to the left here are like waves in the ocean, right? So we're looking at the ocean waves from the top down, kind of coming up to the shore. So that's the way that we can think about what we're seeing here. Now let's say there was a little bit of a gap, like the shore was not perfectly even, it wasn't perfectly flat, there's a little bit of a dip or something. Well, what we end up seeing is that the waves from the ocean will behave in the exact same way as waves of light behave as it passes through this unevenness, or in this case, like in this literal diagram, there's a gap, the light begins to bend a little bit. It's because it can pass through the center faster than what it can pass around the corner. So as the light is passing around this corner, it's going to get kind of caught on the edge a little bit, it's going to splay out, and this is what leads to this curving. Now, if the gap is very narrow, this curving is more exaggerated. So again, light passing straight through the center can pass straight through unmitigated. But the closer the light is to the edge, the more it's going to wrap around this edge, and this curvature is going to become greatly exaggerated, giving us very, very curved light. One way that we can actually see this, like in real life is, I don't know if you've ever done this before. Like this little experiment was first taught to me by Bill Nye, but it's still very applicable today. If you hold your two fingers together, like your index finger and your middle finger, kind of like holding them up in like the Scout's Honor kind of formation, there's a little bit of a gap between your index finger and your middle finger. If you look through that gap, and kind of like into the distance, like especially if you're looking towards a light source, you're gonna see that there are horizontal bands of light, kind of like bright spots and dark spots. The bright spots and dark spots are the result of diffraction as light is passing through the narrow gap of your fingers. So these narrow gaps don't have to be like microscopically small, they could just be as small as the gaps between your fingers. All right, well, what causes then the light bands and the dark bands? Because here we're just seeing light being curved. So like, where are those bands coming from? The bands are coming from what we call interference patterns. As light is passing through narrow gaps and curving, and as a result then interacting potentially with itself, where like if this was the gap between your fingers, you're gonna have one light source and a second light source because light's coming in through multiple points between your fingers. It can interact with itself as the waves build outwards, as we can kind of see on the right-hand side. So these interference patterns occur because of the interactions between the waves. They can either be constructive or deconstructive. All right, so what constructive light looks like, we're gonna draw this in a like simple kind of diagram, and then we're gonna return our attention to the picture on the right. So just put a pin, right, here's my little pin. We're gonna put a pin here on the picture on the right. So constructive light. If we have two wavelengths of light, the first, let's say, just looking like this, right, a generic little wave passing through from whatever the starting point is. If there is a second wave of light interacting with this first, and they happen to, at every distance, at every point in their travel, perfectly line on top of each other, so here I'm drawing this dotted line, this is my second wave, what we actually see is that the intensity of these wavelengths of light they add to each other, they stack on top of each other. As these two wavelengths of light that are lesser sum together, what we see is a new wave that is exactly twice as intense as the starting wave. So here we see these two waves that have each a particular intensity on their own. We add them together and we now have an intensity that is twice as high. So in other words, constructive interference leads to light being twice as bright. Deconstructive is the opposite. We have, let's say here's our distance, our path of travel. We have one wavelength of light, again, kind of moseying along, minding its own business, and coincidentally there runs nearby a second wave of light that is exactly out of phase with the first. It is equally as bright, but perfectly out of sync. These two wavelengths of light will also add together, but now it's like the equivalent of adding +1 and -1. The two are going to perfectly cancel each other out, giving us no light. Now, turning our attention back to the interference pattern on the right, we're removing the pin from this, we can see exactly where light is interacting with each other additively, and where these bands are in between, where the light is deconstructing itself or each other perfectly. Now, if there was an eye over here to sense the light on the right-hand side, what they would see are alternating bands of light and no light, light and no light, light and no light, etc. So again, returning to the example of light moving through your two fingertips in that small gap, the reason why you're seeing the bands of light is specifically because the light either constructively and or deconstructively interfering with itself to give us these alternating patterns of where light is and light is not. All right, so that brings us to the end of our discussion on the nature of light. Now again, we haven't brought anything specifically chemical into the picture yet, but understanding what a wavelength is, what frequency is, and what diffraction is going to get us off on the right foot as we now, in the next section of our lecture, part 2, start tying the atomic back into the picture. The studies that we're about to talk about really focus on how light interacts with matter. So we need to know how light functions in order to understand what studies were being done on how it interacted with matter. But in the meantime, we have a couple of example problems here. Specifically, there are 4 example problems that all have to do with the nature of light. So these problems are really focused on that c is equal to lambda nu, speed of light is equal to the multiple of the wavelength and the frequency. If you would like some more practice with these types of problems, feel free to give the Nature of Light section a try. All right, if you have homework, do your homework, and until next time, class is dismissed.